Hello, my name is Nathan Shauer, and today I'll present the work I've been developing with Professor Philippe Devloo on accurate and efficient finite element simulations of porous media flow in fracture reservoirs. In this poster, I'll first show an introduction and objective, the methodology used, an example, and the conclusion and next steps. The computational simulation of reservoir flow is an important tool that provides valuable insight into the decision process in oil extraction. And along the years, several types of commercial software have been developed with this purpose. However, the majority uses low-order schemes, such as finite differences or finite out volumes. And nowadays, the accuracy of a reservoir simulator is dominated by the accurate simulation of multi-scale characteristics of a reservoir, such as permeability heterogeneity. And to capture these multi-scale features in low-order schemes can be very computationally expensive. Therefore, developing a high-order scheme that is able to simulate fracture reservoir flow accurately and can efficiently capture the multi-scale features of the reservoir can be of great value. Therefore, the objective of this work is to develop a multi-scale finite element methodology to simulate 3D complex fracture reservoir flow that is robust, accurate, and efficient. We are using the finite element method to do the simulation. So the first step is to have a mesh generator and for this type of fracture networks. And for that reason, we developed our own mesh generator called the FEN mesh that is tailored for multi-scale mixed finite element techniques. And in this methodology, the fractures are modeled by 2D elements that are in the interface of 3D reservoir elements. So here in the figure on the left, in gray, there's the reservoir elements that simulate the porous media flow. And in between them, at their interfaces and in 2D, there are the fracture elements that models the flow of fluid inside of the fractures. For the governing equations, we are using that flow in the porous media is modeled with traditional Darcy's equations, and the coupling between flow in the porous media and fractures is based on the conceptual discrete fracture matrix representation. So for the reservoir, we have first here the constitutive law for Darcy's equation. So K3 is the permeability matrix or tensor. Sigma 3 is the flow in the porous media, and P is the pressure. P3 is the pressure in the porous media. Next is the conservation of mass equation, where the divergence of the flow is equal to a source term. And here are the boundary conditions of either pressure or normal flow. Here's the first coupling term, where the flow that goes in between fractures is related to the difference in pressure between the reservoir P3 and the fracture P2. For the fracture, a similar governing equation is adopted. Here, K2 is the permeability tensor for the fracture, sigma 2 is the flow in the fracture, and P2 is the pressure in the fracture. Here is the conservation of mass equation. Well, in this case, it's coupled with how much fluid passes normal to the fracture. So sigma 3n is the jump in normal flow through the fracture. And here are the standard boundary conditions for the problem. We are using a mixed finite element methodology where both pressure and flow are degrees of freedom of the problem. This increases the size of the problem, but also allows for high order approximations with local conservation. And we can at least condense some of the internal degrees of freedom to decrease the size of the global problem. Together with that, we are adopting the multi-scale hybrid mix method, the MHM, which is a numerical technique tailored to approximate solutions with multi-scale features, such as strong permeability heterogeneity. And this methodology also allows for condensing the degrees of freedom into a skeleton mesh. The skeleton mesh is a mesh of an approximation space in between macro elements that are shown here, that they represent the normal flow in between macro elements. So a macro element can have a high refinement to capture the permeability heterogeneity, and all these degrees of freedoms will be condensed into this skeleton to have a decreased size global system of equations. We chose this example to demonstrate the method, which is a benchmark example proposed by Bernd Flemish. In this example, there's a cubic reservoir with 8 fractures, and flow is imposed in this region, this blue region, and zero pressure is imposed in these purple regions. Our multi-scale mixed finite element mesh is composed by the macro elements defined by the black lines, and inside each of the macro elements, there's a fine mesh shown in yellow, and the fractures are in the interfaces between elements shown in red. For some of the results in this problem, first I'm showing the pressure in the reservoir here and the pressure in the fractures here at the right. And I would like to point out, because of the condensing that I talked about previously, the system that would have 96 or almost 97,000 equations can have around 6,000 equations, decreasing the size of the system, the computational time. Next, the pressure is sampled along a vertical line here shown in pink and plotted and compared with some benchmark results. Other research groups try to simulate the same problem, and the results that they achieved are showed in this region in gray and our results in red. And it can be seen that a good matching is obtained for this methodology. So concluding, we obtain a great matching for this complex benchmark problem. And by using the MHM and condensing the degrees of freedom into the skeleton mesh, the final system of equation size can be greatly reduced. And for the next steps, we want to study optimize parallel programming paradigms that are tailored for the MHM. And this is because for each macro domain of the MHM here, it can be solved in parallel in a different core, a different processor, and using an optimal parallel programming paradigm for doing so can lead to a great increase in efficiency of the program. We want to incorporate HDiff constant spaces that we already developed and published about that are optimal for this type of problem. And to accelerate even more, use a locally conservative iterative method that was developed by Jeferson Fernandes together with Philippe Devloo. We also want to study and incorporate constitutive laws for multi-phase flow, and for that, we might use the software OPM. Here are the sponsors for this research, and thank you very much for